Hey everyone, and welcome. Today, we're diving into a concept so simple you can picture it with a pile of dinner plates, but it's so powerful that it's quietly running the very technology you use every single day. Let's get into it. It sounds like the start of a pretty nerdy joke, right? A browser's back button and a calculator. What could they possibly share? Well, it turns out the answer is one of the most fundamental and honestly, most elegant ideas in all of computer science. And that big idea is called a stack. What's so amazing is that it's a concept you can totally grasp in just a few seconds, but modern software, as we know it, just couldn't exist without it. To really understand what a stack is, you don't even need a computer. Nope. All you need to do is picture a cafeteria, specifically a stack of plates. It's truly the perfect real-world metaphor. Think about one of those spring-loaded dispensers. You put a clean plate on top, you take a plate from the top. That's it. You can't just, yank one out from the middle or the bottom. The whole system is built around one point of access, the very top. And that simple limitation, that's the key to everything. So this physical limitation, this idea that you can only access the topmost plate, that gives us the one single simple rule that governs how a stack works in the digital world. And here it is, last in, first out. You'll almost always hear this called LIFO. It means exactly what it sounds like. The very last plate you put on the stack is going to be the very first one you take off. This principle is the heart and soul of how a stack operates. Now, of course, computer scientists have simple, punchy names for these actions. When you add an item, or a plate, to the top of the stack, you push it on. And when you take that top item off, you pop it. That's it. Push and pop. Simple, right? But okay, what if you just want to see what's on the top without actually taking it? Well, there's an operation for that too. It's called a peek. It's like gently lifting that top plate just enough to see the pattern and then placing it right back down. You get the information, but the stack stays exactly the same. All right, so we've got our rules, LIFO, and our actions, push, pop, and peek. Once you know what you're looking for, you suddenly start seeing stacks in action, well, pretty much everywhere. I mean, think about it. Every single time you hit the back button in your web browser, what you're really doing is popping the last web page you visited off of a stack of pages. When you hit Control-Z or Undo in a text editor, you're popping your last action off a stack of commands. And deep down, at the core of how your computer works, stacks are constantly managing how programs run and even how they solve math. Let's actually watch how a calculator might use a stack. So it sees a 3 and pushes it. The stack has a 3. Then it sees a 4, pushes that. Now the stack is 3, 4. Now it sees an operator, a plus sign. So it pops the last two numbers off, the 4 and the 3. It adds them together to get 7 and pushes the result, 7, back onto the stack. Next up, it sees a 2 and pushes that on. So we have 7, 2. Finally, it sees the multiplication sign. It pops the 2, pops the 7, multiplies them, gets 14, and pushes that back. The last thing left on the stack is our answer, 14. Pretty cool, huh? Okay, so we've got the basics down solid. Now let's level up a bit, because this is where it gets really clever. We know stacks are useful, but what if you need to be super, super efficient with your computer's memory? This brings us to a classic problem, the multi-stack. So here's the puzzle. Imagine you have one single fixed chunk of memory. Let's call it an array. But you need to run two completely separate stacks inside of it. How in the world do you do that without being incredibly wasteful? Well, the obvious first thought is just split the array down the middle, right? Give half to stack 1 and half to stack 2, but that's just so inefficient. What happens if stack 1 needs a ton of space and stack 2 barely needs any? You could end up with an error on one side because it's full, while the other side is sitting there with tons of empty, wasted space. Nah, there has to be a smarter way. And the solution is? Well, it's just so elegant. It's beautiful, really. You don't put them side by side. You start one stack at the very beginning of the memory, at index 0, and you start the other stack at the very end. Then they just grow towards each other. This way, no space is ever wasted. A stack only runs out of room when the entire block of memory is truly 100% full. It is a brilliantly efficient design. So, from a simple pile of plates all the way to a super clever memory optimization trick, we can see just how versatile this whole concept is. Let's just do a quick recap of why this simple idea is so absolutely fundamental to computing. So, what are the big takeaways? At the end of the day, it's all about that one simple rule: last in, first out. That's it. And that simplicity lets it power features we use constantly, like undo or our browser history. It's totally essential for how computers handle complex tasks. And as we just saw, it can be optimized in really clever ways to save memory with multi-stacks. It's not an exaggeration to say it's one of the most fundamental building blocks of all modern computing. The stack is just a perfect example of how an incredibly simple idea can have a massive world-changing impact. It really gets you thinking, doesn't it? What other simple, elegant concepts like this are out there, just quietly running our world behind the scenes? Thanks for joining me for this one.